My topic is the RASE knowledge markup, which is a methodology for capturing knowledge. But today I'm particularly going to look at how we present that knowledge. So just an overview, a couple of slides, an overview of what the RASE methodology is about. Clearly we need an ontology of knowledge, and that's a big topic. We need a schema to represent it. We need a representation of how it's stored, but we also need presentations of how knowledge is accessed and visualized. So we can create a taxonomy of knowledge about what kinds of knowledge are we interested in. I think we're used to the idea that there is knowledge embedded in BIM and GIS, which I would call descriptive knowledge, or if it's 4D, it might be narrative knowledge. We can talk about definitive knowledge, such as dictionaries and classifications, and our common assumptions. But my main focus today is on normative knowledge, the requirements such as building regulations, client requirements, and so on. What hasn't been much discussed is the meronymy of knowledge. What are the parts of knowledge? And RASE comes up with an answer that says there are 4 parts to knowledge when you break it down. There are requirements, there are applicabilities, there are selections and exceptions. And these serve to broaden or narrow the scope of the knowledge that you're capturing. And the other way of breaking knowledge down is to say that it's a hierarchy made up of objectives, but ultimately knowledge comes down to individual metrics that you can test in the real world. So RASE has been around since 2007, 2008. You can capture RASE knowledge interactively using a software like Require One, or you can transform existing knowledge, for example, tables of requirements, as in the US Whole Building Design Guide. RASE can be used directly to affect automated code compliance. And again, Require One is a workbench for showing those ideas working. But you can also use RASE indirectly to generate other presentations. And the purpose of this paper is to look at the different purposes that you might want to do that. The kinds of purposes I'm talking about: direct inspection of the knowledge, generation of checklists, consumption by other rule engines, export to interoperable formats, and last of all, formal knowledge representations. So what we're arguing here, or what we're using here, is that knowledge is a tree, that objectives contain metrics and other objectives. What the research paper does is to use simple tree iterator, a simple computer science task, to explore the relationship between RASE and these other knowledge representations. Here's an example regulation. Every blue except matte rectangular door or window, excluding shop fronts, unless in London or temporary and removed daily, shall be fireproof, soundproof, unless a roof light. Now, that's not unusual for the wording of a regulation. It happens to be one I made up a year ago as an example. It is complex. It has spectacularly long sentence. It is obscure with subclauses. It is ambiguous because it lacks punctuation or brackets. It's probably subjective in that things like soundproof are probably not well defined. And it's also unimplementable because it mixes design requirements and operations requirements. So it's a classic bit of regulation that we have to deal with. What RASE does is use color to highlight the roles of the words in that regulation. So the boxes represent objectives. So there's an overall box, which is to pass the whole regulation, but there are smaller boxes to handle some of the clauses and subclauses. And there are underlined words, which are metrics that can be actually tested against the real world. So this is an example of knowledge found in text, highlighted. We can also look at knowledge embedded in tables and other things. But the first way of inspecting knowledge is this direct method using HTML and style sheets. And if you remove the style sheet, it goes back to being the wording in the presentation in the previous slide. The important thing about this is it's still the same document, and it can be reviewed by experts to see if the interpretation is correct. The second purpose is checklists. Checklists is the way compliance checking is done at the moment. So actually we can transform that document to have input fields in it and output fields in it, and the user can fill in the results. And this is generated automatically, and as you answer the questions, it tells you whether you're heading towards compliance or non-compliance, or whether you're still in an unknown state. And we can present that as text, as here, or as a tree, or a list, and so on. And that's really important, because that's the way compliance is done at the moment. And we can give the people an interactive experience to do it. And if you answer one question on that dialogue, you solve the whole regulation. You just say that you're working in London, and the whole thing goes away. Clever. Okay. Another purpose for making different presentations of RASE documents is for consumption by other rules engines. The example that was being published at the moment in the UK, we use Java rules as a rule engine. The one I've shown is a language called, or a rule engine called Datalex. And you can see that a direct transformation has produced some kind of logical statement about what the regulation actually says. And you can interact with it and answer the questions until you get an outcome. Of course, you can use ordinary, I've said Visual Basic, but any programming language we can generate. You can use DMN, decision model notation. You can generate Prolog or Lisp or answer set programming, I think. And maybe we can generate Sparkle rules, spin rules. But the other example I'll show you is visual programming. This is exactly the same regulation, but laid out as a visual program. We could implement it in any of the tools that support visual programming. Although it looks elaborate, there are only three kinds of box: metric boxes, objective boxes, and then data input boxes, and so on. So that could be implemented directly, loaded directly into any of the visual programming tools, and loaded on top of a design application. Another purpose is to export to other interoperable formats. The first one we ever used was the IFC schema, which has a constraint model built into it. And so that was pretty important, that we should be able to get the knowledge into a form, because the applications were already reading IFC models. Now we could actually load in the constraint schema, and then an engine could solve them. Another example of interoperable knowledge formats is knowledge interchange format or rule interchange format. There's a family of these, and they may tie up with semantic web implementations. But the one I've chosen to show is the circuit diagram. What you can see on the right is a circuit diagram using logic gates, as on this chip, to take inputs on the right-hand side and get a logical conclusion on the left, using only a NAND gate. And the chip, you can see, has got 4 of them, so you can see you wouldn't need too many to actually capture that rule. And so circuit is a valid interoperable format. The last purpose I mentioned is to link to formal knowledge representation. And this is sort of expected, and that you should be able to make that connection. And I could show you the propositional logic statement or the predicate logic statement, the first order logic statements, but they'd fill the screen and you wouldn't spot any if it had a mistake in it anyway. So instead, I'm showing you a concept graph. Concept graphs originally were black and white, and they only had solid lines and so on, but it's emerged that actually you need to have logical operators to join the concept graph up. But again, on the right-hand side, in the circle, in the ovals, you have the metrics, the actual tests you're going to apply to whatever your knowledge, your descriptive knowledge source is. Could be IFC, could be anything, could be a human being answering questions. But the logic flow gives you the answer. And again, you may not have to answer all the questions, but the important thing about this is that we can start to validate RASE by showing that it is at least as good as the formal knowledge representations we already have. Okay. I'll pause there. What I should do, which I didn't do at the beginning because I wasn't sure how time would go, but the idea is to try and position RASE and justify it, because it's been used successfully in a number of projects. But until it can be actually explored and linked to the way we do knowledge representation, it's going to remain a theory. So 3 years ago, I presented RASE being used to do automatic rule checking. I came then as an industrial visitor or speaker. Now we're trying to put it on a firm academic and intellectual basis. Okay, thanks.
Okay, thank you. Excellent, Brian.